Hello students, myself Mrs.U.Muthumari, Assistant Professor of Mathematics, SFR College for Women, Sivakasi. So in this video we are going to see about the concept of singularities in complex analysis. So in this lecture we are going to see about what is singularities and the classification of singularities, and we are going to discuss about the methods of various kinds of singularities. Okay, first let us see what is singular point. So for a complex value function, a point A is called a singular point. At this point the function should not be analytic, that is the function is not analytic at the point, but it analytic at some point of its neighborhood. So clearly saying, at a point A the function is not analytic, but at its neighborhood it is analytic at some point of it. So that point is called a singular point. Let us see an example for singularities. Here we have the function f of z equal to 1 by z. For this function the derivative exists for all points but not 0. So at a point 0 the derivative does not exist. So that point z equal to 0 is a singular point for this function. Next, isolated singularity. A singularity point is called an isolated singularity. Then the function is not analytic at that point itself only. That is, that function have the only singularity as that point itself, other than no point on this neighborhood is not a singularities. That is, the function is not analytic at the point A, but at this neighborhood there are no other points at which the function is not analytic. It is called isolated singular point. That is, the function is isolated singularity and this point A itself. There are no other points at which the function is not analytic. At all other points the function becomes analytic. It is not analytic only at the point itself. So in this case A becomes isolated. That's why we call that as isolated singularity. So in this example f of z equal to z plus 1 by z square into z square plus 1. Here there are three singularities are there. Z equal to 0, Z equal to I and Z equal to minus I. So these 3 points are singularities as well as they are isolated too. Because if I consider any open disk for these points, other than these points, at all other points the function becomes analytic. So actually the singularity points are found for what points of function the denominator is non-zero. The denominator becomes 0. At these points the function will not become analytic. So here at the denominator z equal to 0, I and minus I, the denominator becomes 0. That's why we call these points are analytic. Other than these points, whatever the point we consider at its neighborhood, it becomes analytic. So these 3 points are isolated singularities. This is another example. F of z equal to 1 by sin z. In this function, the denominator becomes 0 for the points 0 plus or minus pi plus or minus 2 pi and plus or minus 3 pi up to etc. So for these values the function is not analytic as well as the derivative does not exist for these points, and these points are called isolated singularities. Next one. So we classify the singularities into three types. First one, removable singularities, poles, and third one, essential singularities. Singularities can be classified into these 3 types. Next we see the types one by one. First one, removable singularity. An isolated singularity is called removable if the principal part of f of z at z equal to a has no terms. So whatever be the function is given, if we want to check isolated singularity is removable, we just express the function and check whether the principal part contains z terms or not. Let us see an example. Here, look at this example. Here f of z equal to sin z by z is given. Clearly 0 is an isolated singular point, and let me check whether it is removable singularity or not. For that I am expressing the term, that is rewriting the term sin z by z as 1 by z into I am writing the sin z series z minus z cube by 3 factorial plus z power 5 by 5 factorial, and multiply the term 1 by z within the side, will get 1 minus z square by 3 factorial plus z power 4 by 5 factorial up to etc. Here the principal part has no terms, right? So actually principal part means the denominator should contain the term z, but here there are no terms in which the denominator contains 0. So it is here z equal to 0 is a removable singularity. Let us see another example. F of z is equal to z minus sin z by z cube. Here of course the denominator becomes 0 at the point 0 itself only, so it is called 0 z equal to 0 is an isolated singularity. And let me check whether is it becomes to belong to removable singularity or not. So for that I am expressing the term z minus sin z by z cube. I keep the term 1 by z cube and write the series for sine series expansion, and after simplification I will get the term like 1 by 3 factorial minus z square by 5 factorial plus z power 4 by 7 factorial. And here also there are no terms containing z in the denominator. So here this singularity z equal to z is a removable singularity, that is the principal part has no z terms. Next one, pole. An isolated singularity is called a pole. Here the principal part has a finite number of terms. For a removable singularity the principal part does not contain no terms, and here the principal part must contain finite number of terms of z. For example, f of z equal to tan z. I am checking the singularities type here. I rewrite the tan z as sin z by cos z, and look out the singularities here. The points at which the denominator becomes 0 are pi by 2 plus n pi for all n belong to z. So these are all singularities, as well as if I expand this, definitely the term principal part contains finite number of terms. Here all the singularities are of pole of order 1. A pole of order 1 is called a simple pole, and a pole of order 2 is called a double pole. So this example, all singularities are simple pole. And look at the next example, f of z is equal to e power z by z. So when we are expanding the terms, we will get like this. Here the principal part contains only one term, 1 by z. So this is finite term. So here the singularity is a pole, and only one pole exists, right? Z equal to 0. So it is called simple pole. So no other singularities or exist other than 0. So it is simple pole. And next here is another example for pole. F of z equal to cos z by z square. I keep the term 1 by z square as it is and expand the series for cos z, and after simplification we can clearly see that z equal to 0 is a pole, of course, and the principal part has only finite number of terms, that is 1 by z square only are there, and all other terms, the z term are in the numerator. So it has only one principal term which is finite, so it is a pole of order 1. Here is another example. F of z is equal to z square minus 2z plus 3 by z minus 2. Of course, here singularity is z equal to 2, and when you are rearranging the term, the principal part has finite terms only, so it is also a simple pole. The next one is essential singularity. An isolated singularity is called essential, for which the principal part has infinite number of terms. If our principal part has an infinite number of terms, then we call that singularity as essential. Next, look at one example here. F of z equal to e power 1 by z. Of course, here z equal to 0 is an isolated singularity, but to check whether it belongs to which kind is, we just expanding the series as 1 plus 1 by z plus 1 by 2 square z square plus 1 by 3 factorial z cubed up to etc. Then here the principal part has infinite number of terms. The first term only contains no term in the denominator, but all other terms are having the term z as in the denominator, so it has infinite number of terms here. So it is that singularity belongs to essential singularity. Then next one, here's another example. F of z is equal to z square into sin 1 by z. Here keep the term z square as it is and write the series for sin 1 by z. Then after small simplifications, we can easily see that the principal part has infinite number of terms. There are infinite number of terms in which the denominator contains the term z. So here the singularity is essential singularity. So from this lecture we clearly see that the types of singularities and the method how to classify the singularities. Thank you.